chapter 4. So we're moving on. We've beaten the glycolytic and aerobic and anaerobic. We've beaten it to the ground, buried it, jumped on it. But I have high expectations for the application of that material in the second exam. So, and again, that's the thing that probably I want you to remember 5 years from now, right? Because I could ask you some questions about energy production, and you would get those. Now, one of the reasons why it's so important to go over those aspects of energy production is that it allows us to talk about what types of fuels we're using while we're actually exercising and some of the other things that are occurring that allow for metabolism to meet the demands of exercise, okay? So this chapter, chapter 4, is going to be a much shorter kind of push, but nonetheless sort of, anyways, it's the application of all of the cellular energy production, bioenergetic stuff that we've been learning the last couple weeks. Right? This is how we apply it to the state of exercise. And if we understand it in the context of exercise, then we can understand its disruption in the context of other things like disease or, disease states and stuff like that. And then we can apply why exercise and eating healthy is good for the prevention of those diseases and those types of things. So it just gives us a lens to understand complex physiology, which includes energy production under different conditions and the use of fuels to fuel both cellular and mechanical work. Okay? All right. So, wow, going so fast. Okay. So, a couple things that are really useful. When we are at rest, our blood lactate levels are low. And what does that suggest? That the use of what metabolic system is, or bioenergetic system is relatively low when we're at rest? Anaerobic, what? Glycolysis. Yeah, anaerobic glycolysis. Okay? So, and what's interesting about this is what would be the easiest way for a person at rest to increase their lactate production?
While still at rest?
Yep, sitting at rest. Anaerobic glycolysis is low. Say you wake up in the morning and I take your blood lactate level and it's less than 1 millimole per liter. How can I make that blood lactate level rise? What? That's interesting. I wasn't thinking about that. Suffocate, like take away oxygen. What else maybe that you would do? What? So what's the substrate that's used in anaerobic glycolysis? What? In anaerobic glycolysis, what is the substrate? What starts at the top that we split into 2 3-carbon molecules that we... What?
Say that again?
Starts at the top, we split it, we have a 6-carbon ring. Glucose. So... And our body loves burning glucose. If glucose is in the system, our body's going to burn it. So what would you do to increase lactate levels? What? Eat. Yeah. So if somebody came into the lab fasted, we can do this experiment. It's quite cool. If they're really efficient at burning carbohydrates as a fuel, so say we have a high intensity an athlete that engages in high intensity activity, we take their blood lactate level, say it's 1, 1.2, something like that, and then you just feed them a bunch of pancakes and track one of the things that's going to happen is their blood sugar goes up, but their lactate level also goes up a little bit just as a sheer effect of flooding those pathways with the substrates that it uses, right? The cell's like, well, we love glucose, let's use it, right? And that's going to burn even though oxygen is in the system. Now, is that lactate ever going to reach the level of lactate threshold? No. because we're not exceeding the capacity to do what with the lactate? Buffer it and deal with it, right? But we can increase the level of blood lactate. Now, under resting conditions, it's not that we're consuming more oxygen, it's that our energy demand is low when you're just sitting. So you require less oxygen. So an adult will consume somewhere around 1/4 liter of oxygen per minute. Now, what is that total amount going to depend on? What's the main thing that total amount is going to depend on? Like, between two individuals,
Weight.
yeah, weight, size, body mass, right? So it's better to express it in terms of mils per kg per minute, okay? And I don't want to gloss over this because you're going to have to do calculations using these types of things. And I want to make sure that we're clear about what these values mean so that when we multiply things by like minutes and kilograms, we know what we're getting. Because we're canceling out trading units, things like that, right? You need to be able to trade these things to be able to make certain calculations about energy production, okay? So at rest, the general rule of thumb is that an average adult consumes 3.5 milliliters per kg per minute of oxygen. That's a basic understanding, right? Has anyone learned in their health classes about METs? MET, metabolic equivalents. So you say like 1 MET, or this exercise is 2 METs, or this exercise is 4 METs, these types of things. So 1 MET is what's called a metabolic equivalent and basically equals the amount of oxygen that you consume at rest, which is 3.5 mils per kg per minute. Okay? So if Jordan wanted to estimate the amount of oxygen that he consumed in a 24-hour period, then he would multiply this by what?
Weight.
His weight in kilograms and the number of minutes in 24 hours, right? So 1,440 minutes is 6 times 24. And so then you could get an estimate of the amount of oxygen that you're consuming, right? And what if we knew, on average, how many calories an average person burns per liter of oxygen consumed, right? Then we now have an estimate of your oxygen consumption over a 24-hour period. And if we could get oxygen consumption to cancel and be left with calories, we could make an estimate of your daily metabolic rate based on your body size. Does that make sense? Now again, these are averages, right? If we really wanted to know, we'd have to bring Jordan into the lab fasted, and then we'd just have him sit there and put a VO2 mask on him and say, collect data for an hour, and then say, all right, well, I guess you consume this much oxygen under resting conditions, right? All right, okay. So, one of the most important things that we're going to talk about then is this idea where we're at rest and we're in homeostasis, in essence, right? We may be producing a little bit of lactate, but it's not beyond our capacity to buffer it. We're not maxing out any of our energy systems. We're meeting the demand that is being placed on the system from a fuel standpoint and an oxygen consumption standpoint. We're consuming about 3.5 mils per kg per minute of oxygen. And now, all of a sudden, I jump through that window, land on the grass, and start sprinting across the football practice field, right? There's a transition that occurs that challenges both homeostasis as well as the work demand that's being placed on the system, and we have to transition to that immediately. And understanding what's occurring at that transition gives us a lot of insight into the metabolic needs during exercise. So ATP production increases immediately. Oxygen uptake also increases what would be considered rapidly or quickly, but it still takes anywhere from 1 to 4 minutes to reach what's called steady state. And this is going to be less in somebody that's more well-trained, particularly if they're running at a pace that they're well adapted to, right? So like if I took off at 6-minute mile pace, it would take me a while and I may never reach steady state because I'm not very fast at running 6-minute mile pace. But someone who can run 6-minute mile pace for a marathon very easily, or someone that can run can average 5 minutes a mile for a marathon pace, they could take off at 6-minute pace and reach steady state very quickly. Remember, we've already talked about steady state, which is not the same as we considered sort of homeostasis, but it's a different play on homeostasis. It's a temporary state where we're meeting exercise demand at a given rate in order to sustain a certain amount of work output. That's what considered steady state is, right? And so steady state exercise, which is commonly referred to as endurance exercise, is this state of you're not sitting, you're doing some sort of movement that is typically repetitive, sustained, and at a given or within a range of given rates. And that's your steady state, right? So if we were to bring somebody up on the treadmill tomorrow and let them run for 2 to 3 minutes at a given pace, they're going to get pretty close to reaching what's called steady state. Their oxygen consumption. So like if they're walking at 3 miles per hour, and then all of a sudden we turn up the pace to 6 miles per hour, which is 10-minute per mile pace, their oxygen is going to go up, but it's going to quickly level off and reach steady state, right? And then that oxygen consumption will stay steady for a pretty long time at that pace until they start to maybe run out of fuel or have some changes in their running economy or muscular efficiency or those types of things. And as soon as it starts taking more effort to sustain the same pace, then oxygen consumption starts to go up, and we can see where that is. Okay? So after steady state is reached, the ATP requirement is met often through aerobic ATP production. But that doesn't mean that anaerobic means of producing ATP are completely shut off. Okay? Have we talked about how metabolic systems stack on each other? So to go 7-minute mile pace, I don't know how to spell aerobic. Aerobic, and maybe this much anaerobic, right? So this is going to meet 7-minute mile pace, right? So it's not like this shuts off. It's a misnomer that like when I start exercising, I start running, and oxygen is doing nothing, and anaerobic is doing everything until I get to steady state, and then the anaerobic system completely shuts off and the oxidative system goes on. It's a hard concept to get your head around, but I don't want to mischaracterize how these energy systems work, because typically when undergraduates are taught this, they're just taught these as being in separate buckets, and you turn one on for this type of thing and the other one on for this type of thing, and it doesn't work like that. We're complex biological systems, and these things are always going to some degree, but it's just the level at which they're contributing is going to change based on the demand of the work. Yes?
Of the two anaerobic, the PC one goes first, right?
Well, if like the PCR, the phosphocreatine system is always kind of going as well. But like if I were to just immediately start running right now, those initial muscle contractions would be met through the phosphocreatine system. Yeah. Just because it's our, whoa, what's going on here? Guess we better ramp things up. Okay? So initial production through anaerobic, and then, it's interesting because there is a lag where we produce work that requires more oxygen than what is in the system when we first start exercise. Does that make sense? And this is called oxygen deficit or oxygen debt. So we basically use, if I line up in the blocks and then I take off sprinting, I'm using PCR, my anaerobic system, and whatever oxygen I have in the system until I can get oxygen up into the system and reach steady state. Okay? That's why if you were truly going all out, like the longer you go, the slower your pace gets until you're at like a steady state pace. Does that make sense? Okay.
So at steady state, you can produce more power? Is that?
No, so at steady state, you can produce lesser power for a longer period.
Okay, so like, so when you warm up,
When you warm up.
eventually you're gonna get to your steady state. Is steady state only when you just keep running, or can you,
Yes.
like, so Bolt, for instance, you know,
Yes.
since he's all his power is so short,
Yes.
is a really quick warm up gonna get
He's-
him at steady state, and then
So it's not necessarily warm up dependent.
okay,
It would be Bolt's ability to produce high amounts of power at steady state are not very good
okay.
because all of his systems are for producing high amounts of power
Little time.
outside of steady state.
Okay.
Does that make sense? It's different. It's not about warming up and getting to steady state. So steady state is this state that occurs during endurance exercise efforts.
Okay.
It's not achieved during 100, a 200, a 400, even an 800. By definition, those things are not sustainable. They're not steady state. They're all out, right? And you have, like Bolt is still using his aerobic system to its maximum capacity. It's just that his aerobic system isn't all that great. But this system, these two systems are amazing in him. So when he takes off on 100 meters, he gets a big bump from the anaerobic system. But the anaerobic system, that is, he's producing that power in the absence of oxygen, which means he's incurring an oxygen deficit. Does that make sense? Okay. So there's a lag in oxygen uptake. I take off sprinting, I'm not using oxygen to produce fuel, but I'm still meeting a really high work demand. Make sense?
So when you say a lag, is there any lag in like your work? Like, are you gonna go lower and then all of a sudden it's gonna kick in? You get what I'm trying to say?
Uh-uh.
No.
Say it again.
So when you say lag, you keep thinking like, so when you start off, you're not using your oxygen. Then when it kicks on, is there a space in there where like, okay, like there's gonna be a down effect until it kicks back, like kind of like the, what do you call it, when your second gut or?
Oh, no, that's different.
Okay.
Yeah. So here you go. So if we go from 0 meters per minute, can you guys see this? You okay?
Yes.
Okay. If you go from 0 meters per minute to immediately running at 7 meters per minute, okay, that occurred immediately, right? This is the ATP requirement to meet the demand for, this should say 7 meters per minute, because there's a bunch of these small mistakes in this book. Anyways, so you go immediately from nothing, or I, in this example, I go from immediately doing nothing to now doing 7 minutes per mile, or 7 miles per hour, 7 meters per minute, whatever they're saying here, right? Now, there is a certain amount of ATP that is required to meet that work demand, okay? And I may be capable of meeting that work demand through oxidative means, but I don't have the oxygen in the system to meet that work demand immediately when I go from 0 to 7 meters per minute. Does that make sense? So it takes a little bit of time for my VO2 to go from baseline, which is 0.25 liters per minute, up to 3 liters per minute, which is what I need to meet this ATP demand. Yet, I'm capable of going from 0 to 7 miles per hour immediately. Right? Even though I haven't gotten my VO2 consumption up to 3 liters per minute. And I can't like sit and go and get my oxygen consumption up to 3 liters per minute, then take off running and meet it all oxidatively. It doesn't work like that, right? So all of the energy that was created to meet the work demand of going from 0 to 7 for the first 2 minutes of exercise, this difference, all of this space up here in this triangle, had to be met through anaerobic energy production. Does that make sense? Okay? And then we reach steady state and we go. Now, have we paid back this oxygen deficit once we reach steady state? No. We're just now, we're living check by check at that point, right? We're now, through oxygen, bringing in enough money to pay for the ATP that we want to sustain this workload, right? Now, if we changed pace, we'd have to adapt to that. And that would require a little bit more oxygen debt in order until we got up to the new steady state level of oxygen consumption, right? So if we're running on the treadmill tomorrow and we got these really nice oxygen consumption has leveled out, and say for 5 minutes at 10-minute mile pace, but then all of a sudden I speed it up to 7-minute mile pace, oxygen consumption is going to jump, but it's not going to jump immediately to the amount that's needed to sustain 7-minute mile pace. It's going to go up like this. And in order to make up what's required, because I turn that treadmill and it immediately goes to 7-mile pace, 7 minute per mile pace. And in order to meet that difference, you have to dip into your anaerobic system to make that up, right?
So somebody who has a better running economy they'll meet that requirement faster.
Faster and more efficiently with less oxygen. Yep, exactly. Exactly. Okay, so someone that's in really good shape is going to require this much oxygen to run at 7 minutes per mile, which means they incur very little oxygen debt to get up to steady state at that pace. Does that make sense? And then afterwards, so I run, and then I just stop. Am I producing any more muscular work that my body needs to meet? I'm standing still.
No.
The answer is no, right? But what happens with what still continues with your heart rate and your breathing? They're still elevated for a certain amount of time, right? And what they've demonstrated is that oftentimes the post-exercise oxygen consumption when work demand has gone back to 0 matches the amount of oxygen debt that was incurred to get you going in the first place. Does that make sense? That's called post-exercise oxygen consumption.
So
Or-
you don't pay back your oxygen debt until after you're done.
Correct. So I'm running along, then I stop, I still stand there going, right? And I'm breathing heavy, and that's repaying the oxygen debt that I incurred at the front end to produce the power and the work that I wanted to initiate the exercise that I wanted. But the replenishment of that requires at the cost of oxygen consumption, right? So what are the systems that fuel things like a power clean or a clean and jerk or really strong? What are the bioenergetic systems that meet that demand? Creatine phosphate system and anaerobic if you're doing like longer sets and stuff, right? What do you do when you're done doing a really hard set of power cleans? You're breathing heavy. Your heart rate's elevated, right? You've incurred oxygen debt. Now that oxygen wasn't required to produce, that oxygen wasn't required to produce the energy needed to meet that work demand, but it is required to replenish, and you have to repay that oxygen debt, right? And again, this is tying back in this big picture of all these systems are required to varying degrees to perform, to have optimal performance under different conditions depending on the demand of those conditions, right? So if you just have to do one max lift, you don't really care how much oxygen debt that you incur. But if you have to do max efforts over and over and over again, you better have an efficient system for repaying that oxygen debt in a really quick way so you can continue to put forth those efforts. So oxygen debt is this really interesting sort of requirement. Hey, just real quick, let me do this slide because it ties all this stuff together. So here's our phosphocreatine system. I know we've gone over just a little bit, but just stick with me. So our phosphocreatine system sits at a basal level in the muscle. That's the whole point of taking a creatine supplement, is that creatine, the level of creatine in your muscle gets elevated, so this blue line, these 3 blue dots go up to here, right? That's the whole point of doing this. You increase your capacity that's just sitting there ready to produce work. Then I start doing a maximal lift, and my level of creatine phosphate just depletes very rapidly, right? Then I stand there and I'm breathing heavy and I'm consuming oxygen, and dephosphorylated creatine goes to the mitochondria, gets phosphates added back to it. All of that's being driven by aerobic energy production. Creatine is rephosphorylated and it heads back into the cytosol, and that level starts to come up again, right? This is why you can take a break between reps and replenish your creatine phosphate and then go again, right? Now, what happens is rate of ATP production starts to go way down if you're trying to give maximal effort, because the amount of phosphocreatine has gone down and you haven't given it a chance to replenish, right? And so we meet that initial energy demand through things like phosphocreatine system and breaking down glycogen. And then as glycogen starts to run low and phosphocreatine run lows, what happens to our ability to produce work? It goes down, and we have to produce less power if we want to maintain some sort of steady output. But initially, we can produce a lot of power because we have all these systems that are ready to go, and we can incur a large oxygen debt. But this is why Bolt, even 15 minutes after running an all-out 100, is still breathing heavy. It's because of his unique capacity to incur massive amounts of oxygen debt. And he doesn't have a big aerobic system, so it takes him a really long time to pay that oxygen debt back. Make sense? Thank you.